Okay, in this video, we're going to look at the Laurent series of functions like this one, where the denominator is a quadratic, so it's going to have two singularities. In part A, we're going to find the Laurent series valid in a circular. This is actually an annular region centered at the origin, and this one is a region outside a circle of radius 2. In the previous video, which is our part 2, we saw how to find Laurent series for functions with one singularity. So the denominator here was linear. Okay, so let's get on with this one. So the first thing we're going to do is to find the points where the function is singular. So we're going to do that by factorizing this first. So the factors of this, one of them is going to have 2z here. Now if we put 2 here and minus 1 here, this works out okay. So we're going to write this, resolve it into partial fractions actually. So 2z minus 1 plus b over z plus 2. So if we clear the fractions, this is going to give us 5z equals to a times z plus 2 b into 2z minus 1. When z is 1/2, this side is going to be 5/2. This is going to be 2.5, which is 5/2, and this term is going to vanish. So that tells us that a is going to be 1. The other root is z is -2, which is going to be the singularity of the function actually. So roots of the denominator are singularities of f of z. When z is -2, it's going to be -10. This term is going to vanish. This one is going to be -5. So that tells us that b is going to be equal to 2. So f of z becomes 1 over 2z minus 1 plus 2 over z plus 2 over z plus 2. Okay, so once we have now our function resolved in partial fractions, let's look at the region. So this is the region where mod z is greater than half, less than 2. If we just go to the Argand diagram here, associated with this term, there's going to be a singularity at 1/2. And then associated with this term here, it's going to be a singularity at -2. Just going to do a red circle here. So this is a circle centered at the origin, just touching that singularity, and it's associated with this fraction here. Then I'm going to do a green one at radius 2. So that's a circle centered at the origin. Radius 2 just touches the singularity. So the region of interest is outside the red circle but inside the green circle. So that's going to be the intersection outside the red circle. So remember, the red circle is associated with this partial fraction there inside the green circle associated with that one. Okay, so the way this is going to work then is as follows. Actually, if you check our previous video, what we did say is that if we're looking for the region inside a circle, we factor out the constant. Looking for the region outside, we factor out z, or the z term. So for the red one, the red circle, we're looking for the region outside, so we're going to factor out 2z there. So this thing is going to look like 1 over 2z. Then here we're going to have 1 minus 1 over 2z. And then on this term here, we're just going to use the geometric series result. For this one, we're looking for the region inside, so we're going to factor out the constant, which is this one. So we're going to have 2 over 2. Then this is going to be 1 minus negative z over 2. Then the first term is going to be 1 over 2z into the summation of 1 over 2z to the power n. The second one, this works out to 1. So it's just going to be the summation of negative z over 2 to the power n. So this is going to work out to the first term, 1 over 2z to the power n plus 1. Second term, negative z over 2 to the power n. So n goes from 0 to infinity. We could just leave it like that. What we're going to do though is going to do some calculations that confirm the region of convergence based on the geometric series result. So according to the geometric series, this is going to be convergent in the region where magnitude of this thing is less than 1. So magnitude of 1 over 2z is less than 1. This implies that magnitude of z is greater than half. Then the second one, we want the magnitude of this to be less than 1. So negative z over 2 less than 1. This implies that magnitude of z is less than 2. So of course then these two combine to give us the inequality magnitude of z is greater than 1/2 less than 2, which is the region we are looking for. The other thing to note is that so this Laurent series has got two terms. These are all going to be negative powers of z. As you can see, z is in the denominator. These ones are all going to be positive powers of z. So if you like, this term here is just the Taylor series of this term here, and then this one we get the other series, which is the Laurent series. Okay, so that is part A. We're now going to go to part B. In part B, we want the region mod z is greater than 2. So that means we now want the region outside the green circle. So the region, of course, outside the green circle is also outside the red circle. So for The red circle, the series valid outside, we have already derived that one here. So that's going to be given by this term. So all we need to do now is to work on this term here and look for a series that's going to be valid now outside the green circle. This one was going to be valid inside, so that's why we factorized the constant. So this time we're going to factorize the z. So what this is going to look like, so we're going to have f of z. The first term we have already worked out, so we can just write it there. So that's simply from here. The second term, so now we want to factor out the z, so that's going to be minus 1 minus negative 2 over z here. Actually there is a 2, so it's going to be 2 over z here. Then we use the geometric series result, n plus 1 here. So that's going to be 2 over z, summation of negative 2 over z to the power of n equals to 0 to infinity. This term almost looks like this one, but we can't combine them as they are because this one is negative. So however, if we had a negative there, then we could do so. So what we do is we introduce a negative here, but if we introduce a negative there, then there must be another negative there. Now we can multiply these two. So what we're going to end up with is the summation of 1 over 2z to the power n plus 1 minus the summation of negative 2 over z to the power n plus 1, in each case n runs from 0 to infinity. Then what we're going to do now is we can write this as a single summation term. So the first one is going to be 1 over 2 to the power n plus 1 minus negative 2 to the power n plus 1. Then everything here is times z to the power n plus 1. You can see that this time all the terms are going to be negative powers of z. So earlier we established that the radius of convergence for this one is mod z is greater than 1/2. So we need to work the convergence region for that one. It's going to be the magnitude of negative 2 over z is less than 1. So if we bring z to the right hand side, this is going to be magnitude of z is greater than 2. Now, magnitude of z is greater than 2. Magnitude of z is greater than half. The intersection is going to be outside the bigger circle. So, because you have got magnitude of z is greater than half here, and then you got magnitude of z is greater than 2 here, and then now you can see that the region, of course, that is shaded twice is the one outside the bigger circle. So that's giving us this one, which is of course the required region of convergence. So that is that. Right now we're going to give you a chance to do a similar question. Then we're going to come back and do part C and D. All right, so now we're going to give you the opportunity to find the Laurent series of this function here valid. So we're going to find two expressions, one valid in this region here and the other one valid in this region. So you just want to pause the video and then work through it. Then when you continue the video, you can compare with our solution. All right, I'm now going to scroll down to our solution for this question. Would like to thank you for visiting our channel and watching this video. We hope that the material is helpful to you. We do of course ask you to please do subscribe to our channel to support the work that we do, and if you've got any questions, you can post them in the comment section. So this function here can be resolved to partial fractions taking this form here. The two singularities, one at 1, another one at -4. So in the first instance, we're looking for the annular region in between these two circles. So that's outside the smaller circle which is associated with this fraction, and inside the bigger circle. So for this one, we're going to factor out z. For this one, we're going to factor out 4. So that is how this looks, and factor out 4 there. So then using the geometric series result, this one is going to give us this summation, and that one is going to give us that summation. Then if we bring this negative here, then we can multiply with that -4 and write it in that form. Just to confirm that the series that we have agrees with the region, this one is going to be convergent when the magnitude of it is less than 1, which gives us magnitude z is bigger than 1. This one, magnitude of minus z on 4 is less than 1, gives us magnitude of z is less than 4. These two combined to give this compound inequality. Then for the next one, we want the region outside both circles. So that means this series here is going to stay exactly as it is, but here we're now going to factor out z instead of the constant. So we just bring back this series here, we factor out z here, and this series now becomes like that. If we bring the negative here, we can multiply. So we're going to have negative z to the power n plus 1 there. This becomes positive. This one already satisfied this inequality, and then the one we just did here must satisfy the condition that this is less than 1 in magnitude. So mod z is greater than 4. Now, greater than 1 and greater than 4 intersects at greater than 4. All right, thank you.